Hello, everyone. Thank you for joining us for the next session of 3CQFS. Today we have Chris Fewster joining us. Chris is a professor at the University of York who studies quantum field theory in pure space-time, particularly in the algebra approach. This works on measurement in quantum field theory, quantum energy inequality, in addition to quantum field theory in pure space-time. Today, this will be talking about measurement schemes, observables in quantum field theory. So I'm very interested in fantastic. Chris, please take it away.
Thank you. Well, thank you for the invitation. So as the title suggests, I'm going to talk about something called exact measurement schemes and physical local product states. A lot of the work here really begins with this paper I wrote with Rainer Verch a few years ago on measurement schemes, and then it's been developed a little bit further since. And I'm also going to talk briefly about a recent paper I wrote this year, which was more about Hadamard states. We'll come to that in a moment. And then there are other works in preparation that will be mentioned as we go. So firstly, I hope everybody was paying attention during Rainer Verch's seminar, which I gather was your last one. We have this scheme for measurements, which is sometimes called the FV scheme, after myself and Rainer. And the basic idea is very simple. If we're measuring one quantum field theory, then maybe we should do that by coupling it to an independently prepared probe quantum field theory. And as Rainer told you, well, that actually models what happens in particle detectors. But you could also equally well just think of this as a formal device, as a way of analyzing what's going on when we measure quantum fields. The idea is that by measuring the probe, we get some information about the system, and we'll come to it later. There is an explicit map from probe observables to system observables. So if you measure a certain observable of the probe, when you know the preparation state of the probe, then that corresponds to a specific system observable, and you can then understand its localization properties of that, what we call induced observable. So that's one side of the framework. But the other, equally important, is that you can actually derive update rules for states consequent on measurement, and that is based on operational considerations, and it has a nice side effect that you can prove, for example, that the impossible measurements of Raphael Sorkin are completely absent in this framework. And that's something that Rainer described to you, I think, last time. It's a paper of myself, Henning Bostelmann, and our former PhD student, Maximilian Rupp. What I want to do today is consider a little bit the inverse problem to that. I told you that if you measure an observable on the probe, then there is a defined observable on the system that you're actually measuring. But for practical purposes, you need the inverse problem to that. Suppose somebody gives you a system observable and then tells you, please design a measurement scheme so that what comes out of it is what we wanted, this desired local observable A. What I showed, again, with Maximilian and also Ian Jubb, is that this can be achieved in an asymptotic sense. So what happens here is that, at least in a class of models, including the Klein-Gordon theory, if you take a local observable, then you can design a sequence of measurement schemes, and these are labeled by, for example, natural number n, and you have a sequence then of probe preparation states and a sequence of local observables and a sequence of couplings and so on and so forth. But the upshot of all of that is that when you take the limit of the sequence of induced observables that comes out, what you get is the observable that you were after in the first place. So at least in this asymptotic sense, every local observable is measurable. That's what we showed. And in a little bit more detail, what happens is that, of course, we tune the couplings and the probe observables as n increases. And in fact, what happens is that the coupling strength is even tending to 0 as we do that. And then we have to, as it were, scale up the amplitude of Bn in order to compensate. Otherwise, this would just go to 0. And so really this is a sort of weak measurement in the end of the local observable A. So you get the right expectation value, the variance is all over the place, but you can compensate for that by doing just more observables. And then you can even work out questions like, well, how much effort do I have to put in terms of the number of trials and so on to get my desired local observable to some reasonable accuracy. Okay, so that's what I did in this paper with Ian and Maximilian. But what I want to tell you today is a new idea that gives exact measurement schemes that solve the problem in one go. So you don't need any asymptotic idea of measurement use. There's just a measurement scheme that will give you your desired local observable. So that's the first half of the title. And now I'm going to say something about the second half. And this is all about statistical independence in quantum field theory. So we have our favorite characters, Alice and Bob, and they're going to be working in space-like separated laboratories labeled OA and OB. And they're working on experiments on the same quantum field theory. And for me, quantum field theory is always algebraic quantum field theory. So what they have is a description of the theory in terms of algebras of local observables. Okay, for every suitable region O, there is an algebra that consists of all of the observables you could potentially measure in that region. Okay, so they're doing their experiments. We know, because it's one of the axioms of algebraic quantum field theory, that Alice's observables, because they're in OA, will commute with all of Bob's observables because they're in a space-like separated region. This is sometimes called Einstein causality or primitive causality. So they commute, and therefore, as we know, standard quantum theory tells us that they are then commensurable. So they can both measure the observables they want. There's no problem with that. But of course, just measuring things is not all that an experimenter wants to do. Alice also wants to prepare the quantum field theory in a particular state for her measurements, while Bob is going to want a particular state, omega B, for his measurements. So, of course, it's like having two children. They each want something different. And can you satisfy both of them? Okay, well, let's look into that. Haag and Kastler already thought about this right at the beginning of algebraic quantum field theory. And they said, well, in this situation, what you're looking for is a state on the full algebra of observables for all of space-time, so that when you plug in one of Alice's observables, you get the expectation value in Alice's desired state. Whereas if you plug in one of Bob's observables, you get the expectation in Bob's desired state. So that was their minimal condition. Even that's not really enough, because you want statistical independence of the results of Alice's experiment and Bob's experiment. Otherwise, Alice could somehow tell that there was an experiment going on in a space-like separated laboratory, and that would be a form of superluminal communication. So what you really want is that there should be a state, omega, of the full system, the whole quantum field theory, which has this effect here, so that if you plug in a product of an Alice observable and a Bob observable, then the result is just the product of the expectation value of Alice's observable in Alice's state with Bob's observable in Bob's state. In other words, omega is what we call a local product state of omega A and omega B. Okay, so that's what we would really like. And if such a thing exists, then this is a theory in which it's safe for Alice and Bob to do their experiments at space-like separation without knowing that either one is there. Okay, so there are results about this. There are some existence results that say, well, yes, you can find product states, and these go back to Summers and Werner. And quite recently, there's a result of Coe-Sanders, which is in the specific setting of Klein-Gordon theory. And he says, well, if you you might want a physical local product state. And he shows that, well, in Klein-Gordon theory, the physical states are what are called Hadamard. We'll come to that later on. But Coe shows that there are Hadamard states of this local product form, but it's not constructed from required Alice state and Bob state. It's rather just we start from a given construction, and then we show that there are local product states that are Hadamard. Okay, so we don't really still have a lot of control there, but at least these ones are physical. These ones are more or less physical, maybe not as physical as you'd like. So the second result of this talk is going to be of the following form. If we have space-like separated regions of Alice and Bob, maybe with some little space safety margin between them, and we have physical states, which will be Hadamard, on the theory, then there is a physical local product state of those two, the Alice state and the Bob state, that will do the job. Okay, so this shows that we are able to do experiments at space-like separation without interference. Okay, so moving to some of the technicalities behind this, I'm going to introduce this this abbreviation here, or which is called RUFGO, or if you want to pronounce it, but it stands for Real Formally Hermitian Green Hyperbolic Operator, which is a lot to take on board. All you need to know are the following facts. They form a class of partial differential operators. They act on vector bundles over nice spacetimes, globally hyperbolic ones, and in particular, they've got retarded and advanced green operators. And when we've got green operators, we can form the difference, the advanced minus the retarded green operator, and this we call the Pauli-Jordan operator. So it's just some class of partial differential operators, but includes most of your favorites, the Klein-Gordon field, the Proctor field, which is massive spin 1, the gauge-fixed Maxwell, the gauge-fixed linearized gravity, all normally hyperbolic operators, which are the ones whose highest order part looks like a Klein-Gordon operator, all Dirac-type operators, which are a bit the same. Well, they are the ones that square to give you normally hyperbolic operators. So a whole litany of favorite operators are included in this game. One useful fact about them is because we have a mathematical class of them, we can start playing mathematical games. If we have two such things, we can take their direct sum, which will act on the direct sum of the bundles concerned, and that will also be one of these objects. Okay. Also important is that they can all be quantized, and the recipe is exactly the same one you use for the Klein-Gordon equation. Essentially, wherever you'd have a Klein-Gordon operator, you just put your RUFGO, and wherever you have the green operators of the Klein-Gordon operator, or in particular its Pauli-Jordan, which turns up in the canonical commutation relations, you just put the Pauli-Jordan operator for your RUFGO, and everything else is pretty much the same. What comes out is an algebra that's generated by smeared fields, and those smeared fields are labeled by test sections of the bundle on which you're operating. Okay. Coming back to this direct sum game, we can feed that into the quantization map, and what comes out is just the tensor product, the algebraic tensor product, in fact, of the two quantizations of P and of Q. And we can see how this works at the level of field operators. The smeared field for the direct sum now requires a direct sum of test functions, and what comes out is just, here is the P theory, smeared with F, tensor the unit tensor the Q field, smeared with H. So there's a very concrete way in which you can check easily that this identification between the quantization of the direct sum and the tensor products of the quantizations holds true. If you want to do fermions, then you can. You need a little extra structure, but just as well you actually have it if you're working with suitable Dirac type operators. Okay, so that's going to be our playground today, the rough goes. And what's important is that there is a good notion of Hadamard state, these physical states, at least for what a class of these things which I call decomposable. And this was a preprint of mine from earlier this year. So I'm going to talk a little bit about that, and then we will get back to the plot. So a brief bit of culture on Hadamard states. They are the nice states for Klein-Gordon fields in curved spacetimes. I'm going to work in 4 dimensions. And whatever your curved spacetime is, you can say that the state of the field is Hadamard if its 2-point function takes this very specific form here. So it's got 2 terms that are singular, I should say. Sigma plus is the, essentially it's the signed squared geodesic separation between the points x and y. That's actually only defined when x and y are close enough together, but we can get around that. And this u of x and y, this is something called the Van Vleck-Moretta determinant. We don't need to worry about it, except it's a local, it's determined locally by the geometry of the space-time. Likewise, this v thing is also local in geometric. Here we have a logarithm and some length scale, which is essentially arbitrary. And what's left is smooth. So your state, okay, you imagine all the different possible states there might be of your theory. All of them have a 2-point function with a fixed form. This is fixed, and all of the difference between the different states goes into this smooth bit on the end. Okay, so that's what a Hadamard state is. This was a definition that came out in the 1970s, really. The reason for adopting it is that you've got exactly the same singularities as in the Minkowski vacuum at short scales. If you dig out your quantum field theory textbook, and if you're lucky, it might tell you what the 2-point function is in position space. I think Bjorken and Drell does. If you look in the back or something like that, you will find that it has exactly this form here. And what's good about this fixed singular bit and then something smooth is that you can then renormalize. You can use this to first regularize 2-point functions, take the difference of any of these 2 things, the singular bits cancel out, and what's left is smooth. Then you can differentiate that if you wish. Then you can take points together. And this is how you would define, for example, a stress tensor. Okay, so that's why this is a very useful class of states. As I said, it was developed during the 1970s. It took quite a while to nail down exactly the rigorous form of all of this, partly, as I say, because this sigma plus is only determined near the diagonal and other subtle points about that. This was done by Kay and Wald in their famous paper from 1991. But actually, there was a subtle error that persisted for, as you can see, 30 years and was only fixed quite recently. Very subtle point, but nonetheless, it was slightly needed tightening up. As you can tell, and perhaps the existence of a subtle error that wasn't spotted for 30 years indicates, it's not so terribly easy to work with this, although people did, particularly Fulling, Sweeney, Wald, and Kay. They were actually able to do some things with this, but it was quite difficult to work with. So it was a big revolution when in the 90s, first Radzikowski and then improved a bit by Zalman and Verch, showed that this whole messy business, I mean, with these things here, and this is actually obtained by solving some power series iteratively, all of that can be boiled down to a very simple formula if you know some microlocal analysis. And the microlocal analysis required is that the wavefront set of this 2-point function lives in a particular subset of, it's the cotangent bundle to the product of M with itself. I'll explain the wavefront set in a moment. What are n plus and minus? They are the future or past pointing null covectors on your space-time. And if you start from this just containment result, then actually you can prove rather more. In fact, you can get an exact formula for what this wavefront set is. That was actually what Radzikowski started with, but that would then look a little bit more complicated. This is a very, very simple form of what Hadamard is, captures the whole thing. So when I came to think about these more general rough goes, I was looking for something that would mimic this condition here. And you can do that for what I call decomposable rough goes. And those are ones where this Pauli-Jordan operator has a wavefront set that decomposes. It splits into 2 bits, and each of those 2 bits factorizes. And in the first factor, it has to live in V plus, and in the second factor, V minus, or the other way around. Okay, so this is a particular split form for the wavefront set of the Pauli-Jordan operator. And what are these V plus and minus? They are not necessarily the positive or negative null vectors. It's just some pair of cones that are opposite to each other and which do not intersect. And if you do that, you might think, well, why would you not be interested in nulls? Think of a phenomenon like birefringence, where the nulls, where the photons go perhaps at 2 different velocities, depending on their polarization. So just saying what is null is more complicated in general than it is, say, for the Klein-Gordon operator in space-time. So having identified a decomposable rough go like this, we can then say that a state of the quantum theory associated with that rough go is Hadamard if we have this formula here, which, as you can see, reduces to this microlocal form here in the special case where V plus and V minus are the future and past pointing null covectors. Okay, and this, it turns out, works rather well, which I'll come back to in just a second. So now I'm going to tell you a little bit of what a wavefront set is. So you're getting a bit of an education today, I hope. This is a gadget that was introduced in the early 70s by Hermander and Duistermaat, and it's about the singularities of distributions. So let's start in Rn, take a distribution, take a smooth cutoff, so compactly supported. Then you can multiply chi by u, and you have a compactly supported distribution. Compactly supported distributions actually always have Fourier transforms that are smooth functions. And they're defined like this. You actually take your cutoff function and you multiply it by a complex phase factor. Okay, so e to the I k dot x. This is my convention for Fourier transforms. It works very well in QFT. And then you plug that into your original distribution. And that gives you the value of the Fourier transform of chi u at covector k. So that's how you define the Fourier transform of this cutoff distribution. And we know that the singularities of u, at least where the cutoff is switched on, those manifest themselves in the Fourier transform. If you have a smooth function that's compactly supported, its Fourier transform decays rapidly in all directions. This is not the case if you have some singularities of u. Those manifest themselves in slow decay, or indeed no decay, or indeed growth of this Fourier transform. And a classic example of that would be the delta function, okay, delta at 0. If your cutoff is switched on at 0, then chi of u is just delta, so its transform is delta hat, and that's just 1 everywhere. So it doesn't decay in any direction whatsoever. And there are other examples you can give where you get decay in some directions, but not in others. And that's interesting. So with all of that in mind, we make the following definition. So I'm going to now have a position x and a covector k, which will be non-zero, and we'll define that pair to be regular if you can find a cutoff that doesn't vanish at your position x, and a cone that contains your covector k. And the requirement is that the transform chi u hat should tend to 0 rapidly in this cone V, right? So it's saying that if you go out to infinity roughly in that direction, meaning within that cone, then you get rapid decay. And that's what we will mean to be a regular point for this distribution. And then, having told you what regular is, I'm going to focus on what's not regular. The wavefront set is the set of pairs xk with k non-zero and xk not regular. Okay, so it's precisely pointing out the points and directions where, no matter how tightly you localize and no matter how tightly you draw the cone about your direction k, you will never get this rapid decay that you would see with a smooth function. So the wavefront set then has 2 pieces of information in it. It has a position, which says where the singularities are, and a covector k, which roughly speaking gives directional information about them. Okay, and we'll have a couple of examples. I've already given you the delta distribution. Its wavefront set, the position is 0, that's where the singularity is, and the covectors contain, well, it's any non-zero one, because roughly speaking, a delta function is equally singular in all directions. And you can figure that out from the definition I gave. Here's an interesting one. Suppose you take a smooth function, and we're going to look at the set of points where it's strictly positive, and we'll let u be the indicator function for that set. So it's 1 where it's strictly positive, 0 where it's less or equal to 0. And we also, to avoid pathologies, we say that there are no critical points on that boundary, okay, which would be problematic. Excuse me, if you do that, then the wavefront set can be computed. The position, of course, the positions are all points where phi vanishes. So it's on that boundary where it jumps, right, from 1 to 0. The directional information is actually the gradient of the function phi. Sorry, that should be a script phi at these points on the boundary. So if this was this elliptical thing here, this is what these covectors would look like at every point. They're sort of normal to that singular boundary. And for that reason, I hope that makes the name wavefront a little bit more anschaulich, perhaps. You can understand why that would be a good name for this object to describe the distributions, the singularities of distributions. Okay. So this example, as I say, what turns up in the K is actually a gradient. So it's a covector. And you can show actually that these wavefront sets transform like subsets of the cotangent bundle. And that is the key to doing all of this on manifolds. And this is a great set of tools. It provides precise criteria from when you can multiply distributions together and tells you how you can do it, restricting to submanifolds, pulling back under smooth maps, and also the propagation of singularities in solutions to PD. So this is what Doistermaat and Hermander were doing. But even at that point, back in the early 70s, they knew that there were perhaps applications to quantum field theory. And it really took until Radzikowski for that to completely take off in the 90s. Okay, so back to this generalized Hadamard condition. All of the standard results about Hadamard states that people like can be extended to these decomposable rough goes and this extended notion of Hadamard. In particular, the difference of Hadamard 2-point functions is smooth, We can use point splitting. This Hadamard form propagates under the equation of motion. So if your state satisfies it at early times, then it will satisfy it at all times. If you mix Hadamard states, you get a Hadamard state. You can make pullbacks and get Hadamard still. You can make local operations on your state and it will remain Hadamard. We'll come to another in a moment. The one-point functions are smooth, and you even get some information about the higher endpoint functions. In particular, you know exactly what the two-point function wavefront set is. But in addition to these standard results, I proved a few new things because I had applications to measurement in mind. Firstly, the tensor product of Hadamard states is Hadamard. And then furthermore, partial traces of Hadamard states are Hadamard in this generalized sense. And furthermore, if you have some scattering going on, as we will, Hadamard states are stable under the action of the scattering map. Okay, so these three things are necessary for an application we'll come to now, I think. So let's see how the FE measurement theory looks when we base our quantum field theory on rough goes. So let's say that the system and probe are described by operators P and Q. They could act on different bundles. We want an uncoupled combination of these two theories, and that's obtained by taking the tensor product of the two theories respectively. But we can also think of that as just the quantization of their direct sum. The coupled one is going to be described by another rough go, and that has to agree with P plus Q outside some temporarily compact coupling zone. So if we think trapped between two Cauchy surfaces. And what that means is that T is an operator that just agrees with P plus Q in the far past and in the far future. In the middle, something interesting can happen, and that's where these two theories get coupled together. We can compare the dynamics of these two quantum field theories by a scattering map, which is actually defined on the uncoupled theory. And I'm not going to go into the definition of that. Maybe Rainer talked about it, I can't remember. Then the idea is that you prepare the system and probe independently and couple them together. And then afterwards, you measure the probe and try to infer information about the system. Okay, that's the way it goes. I said there's an exact formula for the induced measurement, induced observable that comes out. And it's done like this. You take your probe observable, tensor it with a unit, put it through the scattering map, and then sort of trace out the probe using the probe preparation state. That's what this map eta sigma is doing. And what's left then is an observable of the system, which is this induced one. Okay, so that is how you turn probe observables into system observables, and you can operationally understand that this is what happens when you measure B at late times. This is the observable that you learn about in the system. That's in our original paper. Coming to the state updates, I'm only going to talk about non-selective measurements today. But if we make a non-selective measurement of some yes-no observable, but then we don't select on the outcome. So maybe somebody's hidden it, the information was destroyed, or we simply ignore it, then there is an updated state that you should use to make further predictions. And you can compute what it is given by this omega ns, and the expectation value of some observable in that state is obtained by another formula, a little bit like what we had before in some ways. You take your A, you now tensor it with the unit on the probe, stick it through the scattering map, and then take the expectation. Here is this probe preparation state, and then we actually tensor that with the initial system state. So this gives a rule for turning system observables into numbers and you can check that it's a state, and moreover, it is the right updated, non-selectively updated state after this measurement. Okay. Now, a very important theorem for what we're going to talk about is the following. This came out of this 2025 preprint of mine, that if we have decomposable rough goes to describe P, the system, Q for the probe, and T, which is the coupled theory, if they are all decomposable, and we start with Hadamard states for the system and the probe, then the updated state, this non-selectively updated state, is Hadamard, and the proof is very obvious now. This is a tensor product of Hadamard states, and therefore Hadamard. This is the effect of sticking that Hadamard state through a scattering map. That is Hadamard. And then all we're doing here, of course, is partially tracing it. And we know that partial traces of Hadamard states are Hadamard. So the whole thing works out that this omega ns, non-selectively updated state, is itself a Hadamard state. So the tagline here is that non-selective state updates of physical states are physical. And that's an important consistency result for two things, actually. It's a consistency result for the measurement framework, because if you went round non-selectively updating physical states and got something non-physical, you'd have a problem. But it's also a consistency result for this new idea about what Hadamard states should be. The two mesh together in a nice way. Okay. Now I want to start moving towards solving the two problems I started with. One, of course, is to get these exact local measurement schemes, and the other is to prepare local product states. And we're going to, we need another set of tools, unfortunately, the last set that we need to introduce, and that is based on gauge transformations. And if you happen to have a real Lie group acting on the bundle on which your rough go acts, and your rough go is even invariant under the action of the group, then the theory, the quantum field theory, has a global gauge symmetry under that group. And what do we mean by that? Well, there has to be a homomorphism from the group into the automorphisms of the of this algebra that we get, the quantum field theory, which interacts like this on the quantum fields. So the action corresponding to group element G on this field, I think you can ignore that M altogether, sorry, that's a vestige of something else. Acting on the smeared field phi p is the smeared field, but where we act with our Lie group element on the test function F, the test section F that labels our field in the first place. So that gives us a way of acting by the group on this algebra. And that turns out to be a homomorphism. And a good example of this is the following. Take any rough go, then we can take its direct sum with itself. That's still a rough go. And then there's an SO2 gauge symmetry, because we can simply rotate these two copies of P among themselves and with a rotation matrix. So, and that is actually then a symmetry of this rough go. So whenever you have a P plus P theory, then there is an SO2 global gauge symmetry. And the trick we need is that every group element in the identity component of the Lie group of this sort can be realized by a scattering map. And the argument for that is quite simple, so let me explain it. Well, firstly, take any smooth function from your space-time into your group. And then you can use that to give a local gauge transformation on sections of the bundle. So what we're going to do now, you give me an element, a group element in the identity connected component of my group. I build a smooth function that is the identity in the far future and your chosen group element in the past. And I can do that because it's identity connected. So I can sort of make a smooth deformation from constantly identity to constantly G. So I do that, and then I get a local gauge transformation that reflects that, and I can transform my rough go P under that action. And in the far future, of course, it's the identity. So I'm not doing anything and I get P. In the far past, I'm conjugating with this constant group element. And P is assumed to be invariant under global gauge transformations. So this also is equal to P. So this new operator Q is equal to P in the future and in the past. And it is actually also easily shown to be another rough go. And we can compute its green operators easily, and they come out in terms of the original ones and this gauge transformation. Very nice. So we can actually say this agrees with P in the past and in the future. So there's a sort of scattering map that describes it. And when you do that, you find that the scattering map that describes the relative dynamics of the Q theory relative to the P theory is just the action of this global of this gauge transformation, but now for a constant element G. Okay, again, ignore the M. Sorry about that. Okay, so that's very useful because it gives us a way of transforming things by scattering. So here's the example that we're really going to focus on. The system and the probe are both going to be copies of the theory coming by quantization of P. We've got an SO2 symmetry of P plus P. So we can arrange a coupled combination whose scattering map is exactly acting by some rotation, okay, on this doublet of test functions. We do that just by making it the theory from the previous slide, but applied to P plus P rather than just P. In particular, we can be interested in two special angles. If we plug in angle pi by 2, it turns out that the effect of this scattering map is to flip A tensor unit to unit tensor A. On the other hand, it turns out that if we use angle minus pi by 2, it flips unit tensor A to A tensor unit. And that's very useful little gadget to have. If we now compute the induced observable map, we're using this minus pi by 2, then we see the scattering map is just going to flip these round. So I need to evaluate this one, but this is just tracing out that operator, and it gives you just a factor of 1. So we just get B. So in this way, we see that if you want to get observable B out, then you just use this measurement scheme that I've described and plug B in to the probe. This is kind of stupid, and we will improve on it in a little bit. But it does show, at the very least, that there are measurement schemes that give you every local observable. There's a hitch, which we'll come to in a second. Let's look at state updates. Let's look at S is plus pi by 2. Well, in that case, it flips around things in the other direction. Here is the formula for the non-selectively updated state. Remember, we have this form here, but now we're flipping this one into there, so they just flip around. We can compute this. The original state just evaluates on the identity and gives you 1, and we get the probe preparation state. So this is another slightly stupid protocol. It shows you that if you could prepare exactly the state you want on the probe, then you can prepare it exactly on the system by doing this non-selective update using this measurement scheme. Okay, so on the plus side, every local observable has a measurement scheme and every state can be prepared. But the hitch is that these sort of universal protocols require you to control a full Cauchy surface in space-time. And the reason for that is this picture here. This was a slab of space-time running, right across the whole universe, if you like. It's bounded in time, but potentially unbounded in space. So you don't typically have that level of control, or good luck to you if you do. If you did, you would be able to implement these protocols. So what can we do about it? I'm working with Benito Juarez Aubry, and we have a localization result for these measurement schemes. So here's space-time, here's some time-bounded slab in it, and we can consider two coupled variants of a system theory tensored with a probe theory, and they're both going to be, the coupling in both cases is going to be somewhere in this slab S. And the theorem is the following. Suppose these coupled theories, although they may be different, suppose they agree on this Christmas tree region, L, right? So this whole funny region here, Christmas tree. Supposing that the coupled theories agree there, and of course out here in the future they have to agree with the uncoupled theory as well, and the way in which they agree has to be compatible with that. Suppose that you have a probe preparation state for C and a probe preparation state sigma prime for C prime. They only have to agree in the base of the Christmas tree. And suppose your system states, they could be different system states actually, but suppose they agree in this region L minus. Then the upshot is that the induced observable map using C and the induced observable map using C prime, and they're possibly different preparation states, they agree on probe observables localized in the tip of the Christmas tree. Okay, so when this is in your out region, this is where you want to have your probe observables living. So the two couplings will give you the same induced observable. Moreover, the non-selective updates of these possibly different initial states resulting from possibly different coupling theories, they coincide up here. Okay, so you can get local experimental control in this way. This is actually quite good because, of course, if you're doing an experiment, you may have arranged couplings and so on in your lab, but who knows what else is happening outside the laboratory. And so you never really know what theory you are dealing with. So this actually removes that, as it were, loophole in the measurement framework. Okay, so we're going to use that in the following way. We also use the trick that two Hermitian fields described by P can be thought of as one complex field with the same equation of motion. The SO2 gauge group on P plus P then turns into a U1 gauge group on this complex field. So now we're going to say, suppose that this complex field can be coupled to an external electromagnetic field. And that's a way of getting local U1 transformations into the game. And I'm going to call the coupled operator PCA, P because it was based on C, C because it's a complex region, A because it's got this external electromagnetic field potential A in there. If we have just a pure gauge vector potential outside some set, then this actually turns out to be a coupled variant of, well, P plus P, or P regarded as a complex field, and the coupling zone is just K. The global protocols that I described earlier can be written in terms of exactly this sort of operator. We're using a vector potential, which is just the gradient of chi. Actually, I may have missed a sign, but that doesn't really matter much, which is just the gradient of psi, so pure gauge vector potential, but not constant. It's constant outside the slab, inside something interesting is happening. It's interpolating between the identity and your desired group element. And what we do to localize this whole protocol is simply take that global, that pure gauge thing, and multiply it by something compactly supported. So quite a simple idea. Diagram gets a little more complicated though. Here is our Christmas tree that we had before, okay? And S is the slab where our global protocol was running. And I'm going to choose a purple function psi, and its support is in the purple region there, okay? So what I do is I look at the coupled theory, which is obtained by taking the external electromagnetic vector potential psi times chi, gradient of chi. And since psi vanishes outside the purple region, then of course this is completely switched off outside the purple region, and everywhere outside there it simply reduces to the original theory, just PC of 0, which is equivalent to P plus P. Using the localization result, we can immediately realize that the measurement scheme we get with this localized coupling will give us what we wanted, at least for probe observables localizable in the tip of the Christmas tree. In other words, if you want to measure local system observable B, then you measure that on the probe, and so B has to be localizable up in this region, and the induced observable that comes out is just this B. Okay, so that's how you do it, and one can also say, this is using something called the time slice axiom, that all observables localizable in this region N, those are equivalent to things that, okay, bye, Magdalene. All those are equivalent to things that are localizable in L+. Okay, so that's how we measure things localizable up here. What about measurement schemes? Oh, but just one last point. I want to re-emphasize the fact that the coupling is now in a compact region, and that's something that you could expect to control. Okay, so now what about physical state preparation? We're going to use the same coupled theory, and we now have a system and a probe preparation state, omega and sigma, and I'm going to use this, again, local coupling to determine a non-selectively updated state. And then what we'll find is it has to agree with what we would have got from the global protocol. So in other words, it agrees with the probe preparation state on L+. And something else you can prove is that it is completely unchanged in the causal complement of the coupling region. That's actually a result from the original paper with Reiner. So we're getting somewhere. We can allow Alice to build the state that she wants. Okay. So now let's put Bob in the picture as well. Bob is at spacelike separation. He's got his own Christmas tree in space-time. And we now run the thing as before. So we have initial system state omega. Alice has preparation state sigma A. Alice has her own coupled theory. Bob's got his own coupled theory. Alice's update gives what she wants up in that tip of the Christmas tree. And out in Bob's region of space-time, it just gives the original system state. Okay, moreover, let's suppose we take an Alice observable and a Bob observable from these regions here. We can compute the updated state on the product. It's an explicit formula. The scattering map for Alice leaves Bob's observable alone, but it flips hers into the other factor. So we get this. And now we can compute the answer, and we just get the product of Alice's expectation in her preferred state on X and the original system state acting on Bob's observable. Okay, so we'd already be done if we could have started with the initial system state in Bob's preferred state. But we can do a bit better than that. Now Bob is going to do an update as well. He's going to use preparation state sigma B. We have, because these coupling zones are spacelike separated, an idea which is called causal factorization. So the total scattering map for these two couple theories is actually going to factorize into a bit for Alice's and a bit for Bob's. And then you can run the calculation as before, this total scattering map now maps XY actually tensor unit into unit tensor X tensor Y. And that's what happens if you let this scattering map act on XY. And now when you evaluate that, you see that omega hits the unit, so it's 1. Sigma A hits the X, so we get that. Sigma B hits the Y, so we get that. So it's a local product state. And now, to finish it all off, if omega and sigma A and sigma B are all Hadamard, and there are various other adjectives you can throw in as well, then so is the this non-selectively updated state. So in other words, there are physical local product states, and I've told you how to build them. So using couplings with compact support and any initial state, because the original state of the system is nowhere there, right? It's not involved at all in the final answer. Alice and Bob make independent, non-selective measurements. They each use their desired state as a preparation for their probe, and the overall updated state is a local product state of their desired states for these tip regions, LA plus and LB plus, and it is Hadamard if all of these original states are. Okay, so that's what I wanted to tell you about. Here's the summary. I've shown you that for a large class of models, those rough goes that you can couple to an external electromagnetic field, all the local observables have measurement schemes where you have a compact coupling zone, and we can prepare physical local product states. And the protocols are operationally clear. So not only do physical local product states exist, they can be prepared. And the payoff from all of this is just as well. That means that the world is safe for experimentalists, at least if they're using rough goes. And with that, I thank you for your attention.
Thank you, Chris. Do we have any questions?
Yes, I have a question. So this local product states the statistical independence between measurements performed by Alice and Bob.
Yeah.
So I'm thinking that sounds a bit like Alice has performed some sort of swap operation in her region between her probe state and the shared field.
Yeah, that's exactly what is happening, right? So where are we? So you see it here very clearly, right? So here's the update, the state preparation. The scattering map is precisely flipping the system into Alice's probe field. Okay, so that's what's happening at this global level. But the idea of the localization result is that this can even be done at the local level.
Right. Okay.
So, I mean, the idea that you can use swap maps in measurement schemes and state preparation is, of course, sort of known in quantum measurement theory, sort of obvious, and it's sort of regarded as a little bit of a stupid way of trying to show that you can measure everything. But here, what actually happens is you can make it local. And at a physical level, you could say, right, supposing you can couple to an external electromagnetic field, then you can even say what the coupling is. So you really could imagine going into a lab and designing, if you can set up a particular external electromagnetic field, then you can do this.
Okay, that makes sense. All right, thanks.
So I want to just clarify the role that the gauge is playing here. So it's mainly to show that the non-selective outcome is gauge invariant.
So the reason, it's a bit of a trick, really. I'd settle for any old interaction that managed to give me my measurement schemes. What I'm looking for, of course, I am trying to build this out of these swap maps. So anything that gives me a way of implementing a swap map through, well, in the first instance, a global scheme, and then which I can then localize, is something that would do the job. Okay, and it was something, in fact, we realized in the earlier paper with Maximilian and Ian. We actually give it as a proof of principle that you should be able to do something. We gave an example like this, okay, because it allows you to rotate things around. Now, the reason that we didn't just say, oh, that's it, job done, in the other one is that, well, it does require this global control. And so there we went off and showed, well, you can do it by other means in an asymptotic sense. And what I'm doing here is going back to this proof of principle and saying, well, actually, maybe we can localize it and also give a physical understanding of how you might be doing it in terms of the fact that this is a U1, and therefore you can really think of that as coupling to electromagnetism. So that's the idea. It's a convenient way of doing it. To a certain extent, you know, you could still raise a criticism that, well, how on earth did Alice manage to prepare her desired state on her probe system? I'm not, of course, I haven't really explained that. What I have said is that if she can at least prepare it well enough, then it can be combined with Bob's probe state, and they will get what they want. I suppose, I mean, so there are potential criticisms here. I think it's still saying something because it says that if whatever Alice's probe state was and whatever Bob's probe state was, what comes out of this protocol is a local product state of those states. Okay, so that's saying something. And also, it is a proof that every local observable has a measurement scheme, and that's a point of principle, right? To determine that, you could then, of course, go and look for other ways of doing it, but this proves that it can be done.
Okay, thank you.
I might have missed a step here. Does the probe have to be the same as the probe field? Does it have to be the same as the underlying field?
Yeah, in this example, it is. Yeah. Okay. So this way of doing things, you choose the system and probe are both copies of the same field.
So, but in theory, you could take a different probe field, but as long as it obeyed the same algebraic properties in the interaction zone. That's
right. So in the general framework, there's no reason that you have to have the same probe theory. And indeed, you know, even in that paper, we gave examples where they differ minimally because they were Klein-Gordon fields of different mass, for example. But you can certainly have measurement schemes in where probe field is not at all the same as the system field. However, what I was after was to build a particularly simple way of realizing the swap. And for the swap, obviously they have to be the same, or contain, it could contain part of a part that was isomorphic to the system, I suppose. But you need some commonality to be able to write something as simple as this swap map. Okay, but again, this is just one way of doing it, and the importance of this is to say that, look, it can be done. And you could, of course, just be interested in the question, are there physical local product states? Answer, yes, there are. And not be at all interested in how you get them. But if you are interested in how you get them, then this is one way of getting them.
Thank you very much. No, this is a very cool result. It does answer, yes, as you say, both existence and a method, which is great.
Yeah, thanks.
An operational.
Sorry?
It's an operational scheme.
Yes. Yeah.
Excellent. I have any further questions? I don't think anyone else does. So thank you again very much for giving this talk. It was
Thank you.
very nice to learn more about this.
Excellent. Okay, good to see you again, Evan. And Albert, and well, I don't know if I've ever met Nico. Anyway, nice to meet you.
Thank you. Bye.